start? Yes, we are live, so the stage is yours. Thanks.
Okay. All right. Thank you all for coming. It's a pleasure to organize a session at International the SPM. We have a really exciting lineup of speakers. I won't speak for very long so that you can hear them. They have much more interesting things to say. So our first speaker today, okay, give me just 1 second to make sure that I have make sure that the speakers are all, okay, sorry. Okay, problem solved. Okay, so as I was saying, sorry for the hiccup. Our first speaker today is Inbar Sarausi. She's coming from the Weizmann Institute of Science in departments of mathematics there. And she's going to tell us about lower bounds on generalization error of deep learning models. If you have any questions, feel free to ask in the chat and I'll ask them to Inbar in the end. If there's a way, I'll let you speak also. We'll see how it works. If you have questions, please go ahead and ask. Inbar, the stage is yours. Thanks so much for
Thank you very much for the introduction. Okay, I will share my screen. All right, so today I'm gonna talk about our recent work where we derive lower bound on the generalization error of deep neural network. In particular, we show that the unbiasedness is not a reasonable requirement in high dimension. And we provide lower bound, which we calculate using random matrix theory. So this is a joint work with Professor Fazantuni from the Weizmann Institute. All right, so let's start. So in machine learning today, there is a big mystery regarding generalization. In particular, if you look at the generalization error as a function of the capacity of your hypothesis class, which can be measured, for example, by the number of parameters. In classical machine learning, you would used to think that there is some kind of a sweet point in which you need to stop training your model. And this is the best point in which you generalize, but actually this turned out to be not the complete picture. And nowadays people train over millions and billions of parameters, and we are still able to generalize quite well. So almost most of the machine learning today is working in this over-parameterized regime, and this picture is actually also for linear models, not just for deep neural network. So this was kind of motivation for thinking about this work, and in particular, what we start asking is, can we find a lower bound? So why basically a lower bound? Because calculating the actual error is possible only in toy examples, and even if we have such a lower bound, maybe we can use it to as a benchmark and guideline to improve our experimental design, which is also something that is kind of random today. And maybe we can understand some characteristic properties and limitation of the model that we are studying, and this is what I will show you today regarding unbiased estimators. And I would like to state that this is a parallel view to the existing upper bounds in the literature, mostly in computer science literature, which are based on complexity measure. And in particular, it's interesting to see the connection between the two. And another requirement that we have is how as we would like that this bound will be true for as largest estimator as possible, so almost for any algorithm. Okay, so let me start with a bit of convention annotation. So we are working in a supervised learning problem. So we have the training data is composed of MIAD samples, which are drawn from some parameterized distribution, and the number of parameters can be extremely large. And in particular, we assume that there is some true function that describe our data, and the measurement are noise by some Gaussian noise. And the feature distribution is not dependent on the parameters. And the test data is composed of a new example, which is drawn from the same distribution. And we take it without noise because we want to measure zero error. And what is our goal? Our goal is to find an estimator, to find an algorithm in which which will be a function of my feature vector and new feature vector and my training data, and will minimize the generalization error. And note here that I'm not asking for an estimator for the parameters that I have, but I'm asking for an estimator for the function of the parameters. And in particular, I'm not also considering a plug-in estimator. So it's a very general form. For our context, we will consider the mean square error. And for that, it is well known that the optimal estimator is the conditional expectation. But this is also an object that is extremely hard to calculate if you're thinking about a nonlinear model. And usually the generalization error that we are in here is as follows. So we say that the generalization error can be decomposed into two orthogonal parts: the variance of the estimator and its bias, when the bias is defined as the average of the estimator over all training data minus the true function. And note that using this definition, the optimal estimator can be biased. So there is no, so this definition does not rule out this exception. And this is already suffice for me to state our first theorem, in which what we show here is that the generalization error is bounded from below for any unbiased estimator by the variance of the noise of the measurement times the expected rank of the Fisher information matrix divided by the number of samples. So the rank, so the Fisher information matrix is a well-known matrix in information theory, and note that here it can be extremely large. It can be of the size of the number of parameters that I have. So what is actually surprising here is that the bound is basically dependent on the rank, which is extremely sensitive object to small eigenvalue perturbation. And this is what I will show next for specific model. And now that this is also true for this result is actually true also pointwise. So here we did not even need to assume prior on the distribution of the parameters. And let me clarify what we actually signed here is basically that if you have a small bias, then that means that the error can still be small. But if the bias is strictly zero, then the error can shoot up. And know that if we compare it even to the null estimator, in that case, unbiased estimator will be worse than that. All right. And so how do you prove such a result? So unbiased estimator just means that we average over the average of the estimator is equal to the true model, and in that case the error is just the variance of the estimator. And now we would like to apply Kramer-Rao lower bound, but you encounter into a small problem. The Fisher information matrix is not necessarily invertible. So what can you do? You need to project into the right subspace, and once you do that, after a few algebraic manipulation, you arrive to the rank of the Fisher information matrix. All right, so let us take as an example and neural as the function f of theta to be a neural network. So in that case, just setting the notation, I have a set of feature vector and a set of weight and biases, and which is represented by these lines, and the circles here will represent the activation function, and the parameter theta in that case will be all the parameters of my model. And activation function can be the one of your choice, sigmoid, ReLU, and so on. All right. So in this case, what we can show is that if we take a linear deep neural network for any number of layers, then the expected rank will be essentially the rank of the covariance matrix. And this is this is an example for actually into the case in which you have a lot of parameters, but in the end the rank is still small. And if the rank is if the covariance is identity, and if D is very large, then this quantity can be very large. And the intuition for this is that basically, in the end of the day, even though I created a very complex model, I essentially have a linear model. And now what is more interesting is what happened for the nonlinear case, if you have a nonlinear deep neural network. So in that case, what we can show is that the expected rank is basically of the order of the number of parameters that you have, which for neural network is for the order of d squared, which is extremely large. So basically in that case, the error can be very, very large. What does that show you? It shows you that having nonlinearity is actually pushing you towards solutions that are biased. And basically estimator in this over-parameterized regime tend to be biased. All right. So basically assuming that the estimator is unbiased is not reasonable. So provide a bound for any estimator. So what we do is basically assume something on the data. So basically we consider a data that was generated from a neural network in this linear width regime in which both the parameters and the samples and the observation and parameters and the size of the hidden unit and the feature is of the same size, the same order. And so for any estimator that you can think of, what we can show is as follows. We have the following bound, and these bounds are actually dependent on the ratio between these dimensions and on the activation function. So here it looks like a bit complex expression for which we derive in this limit, and this is where we use the techniques from random matrix theory. And so let me just focus on the bound themselves, and I will show you a few features of them. So one interesting point about why do we actually have two bounds? So the reason for that is that in order to get the largest bound, we had to estimate to assume that we estimate the first layer and fixing the second one. But in the end of the day, we are giving a bound when all the parameters are being learned. So this is just for the proof technique. And another point is that there is no dependencies on the size of the hidden unit as long as it's large. And another interesting point here is that even though my model assumes some variance over the noise, in the end, even if we take it to be zero, we still get an error, meaning that there is some ill-posedness in the model itself in which it does not allow me to estimate the metrics of the first layer. And for the second bound, so you can already guess that it's basically by estimating the second layer and fixing the first one. And here this is kind of similar in a way to techniques we can use techniques from the random feature model. And in particular, it's an interesting question whether this bound can be is tied for. We conjecture that it is tied for the random feature model. All right, and so now this is very nice and to have this bound, but we actually want to compare them to some real estimators. And so in particular, having an analytical expression is not something that is accessible in this limit. So what we did is we basically did a numerical simulation. So we generated data that is from a neural network and added noise. And then this will be like the teacher network. So it's kind of working this teacher-student network. And then we apply an algorithm. So in that case, we have a student network, which is also a neural network, and we run stochastic gradient descent. Okay, so what do we show? So basically, what you can see here is the error of stochastic gradient descent as a function of the ratio between the number of features and the number of observations. So first thing you see, and in green you can see the bias of this estimator, and basically you see that the stochastic gradient descent is biased. So at least for the examples that we show, so this is kind of goes along with our theory. And another point is that deciding which bound is better, if you estimate the first layer or estimate the second one, it's not possible, because it really depends on the structure of the activation function and on the parameters such as the ratio of the noise and on the noise. So, sorry. So basically, and another point that is kind of interesting here is that basically these bounds are actually in the right order. So they are they are kind of close to the true error. This is without even optimizing over stochastic gradient descent. And here you can see it for different value of the noise. So you can see that we are actually really predicting something about this error, and it will be interesting to explore this further. Where does this gap come from? All right. So with that, I will finish. If you have any questions, and here I attach here our preprint of the work.
Thanks so much, Inmar. Well, if anyone has questions, we have a couple minutes for questions.
Hi.
Yeah, go ahead, Joe.
So I have one question about the grammar, in particular the invertibility. So there's this idea that if the Fisher information is not invertible, then you go to a higher order derivative. So the Fisher information is like a second order derivative of the, you know what I'm talking about, right? And then if you want to bound it, you go to higher orders. Have you tried to look at this or something like that?
The problem of invertibility comes in the case of unbiased estimator, and in that case we show that even for the first order, for the second order, in that case, it's the error is exploding. So if I understand your question, accessing higher order derivatives does not give us more knowledge in that case. And in the other case in which you have for any estimator, the second lower bound. So in this case, we did not explore higher orders, but there is no problem of invertibility because of the prior that we assume over the parameters. But it can be interesting to explore bounds that will be depend on higher order of the derivative in that case.
Okay.
So
thank you very much.
There is a question from an attendee. Someone raised their hand, but I don't seem to have the ability to give them permission to speak. Is someone from the tech team here that can? Otherwise, I would ask the attendees with questions to write their questions. So I see the raised hand, but I don't see any option to give them like speaking permission, because I'm not the host of the meeting. The host of the meeting is the tech team. Is anyone here from the organization?
Yes,
no? Okay.
sorry, I'm here.
Yes. Okay, good. So if you can give permission for there's someone with the raised hand in the participants.
Okay.
Because I don't have this.
No, neither do I. I always have to ask the technician, but that's possible. So just need to be a little bit patient.
Yeah, that's okay. So I'll ask a question while
sorry.
we're waiting then. Yeah, no problem. So Inbar, on your when you had your experiments on the graph, can you go back just a slide back?
Yeah.
Why is it that the black line and the green line don't meet at 0? Like, isn't this when you have like infinite samples compared to input size? And so why should there be any variance in the algorithm? Or am I like, is this intuition not?
Why won't we? I don't have actually an intuition, but from what I think is that there should be a variance, right? I mean, if the variance was, I mean, if the lower bound, I mean, if there was no variance, I guess that, I mean that would.
But somehow, but in the sigmoid and the right, so both in the sigmoid and the hyperbolic tangent, they meet, right?
You mean the bias and you mean in a very low, yes, you mean here?
Yeah, I mean on the far left.
Yeah, I mean, I guess it's a if I will take it to infinite number of samples, then if I continue to graph, they will probably meet. Yes. Yes. So yeah, that's a good thing.
Because this is probably, I mean, maybe not easy, but it's potentially a limit that one can study.
Yes, but in some sense, we wanted to I mean to explore the other limit in which you have like a lot of parameters, because this is like more like the classical limit.
Right, I understand. Okay, thank you. So I think
but
so.
It's true that on that case, yeah, you.
So
interesting.
The participant can ask the question now, I think.
Okay. So yeah, go ahead. I now can see who it was. So are they? Oh, it's Robert, right? Robert, if you're here, you can go ahead and ask your question. I can't hear anything. I don't know if the issue is on my side.
Either. Yeah.
Yes.
On my end, it seems it's just not connected to audio.
Yep.
Should we see him in the meeting or I
don't. Yeah, I see.
Should be in the panelists now to be able to speak.
Okay, so here's what I propose. We go to the next talk, and then we let Robert ask the question to Inbar. You're going to be around for the next talk, Inbar?
Yes, yes.
Okay, so if we find a minute or two, we'll just can ask him his question afterwards. Okay, so we'll go to the next talk. Who now I have to go see who it is. So this is Anya Katsevich. So if Inbar, if you can stop sharing, then Anya can share. And
all right. One second.
Yeah, take your time.
I think it's connecting. There's something loading.
Yeah, this is. You have the whole setup in Portuguese. I think. It is saying that it's loading. Yeah. If it gives you trouble, I mean, there's also a direct Zoom link that I can send you.
Okay, I mean, maybe I should try to close it and reopen.
I'll send you a direct Zoom link to your email address.
Anya should already be on that direct Zoom link. She's a panelist, so the Zoom link is for the panelists. Is this a problem of your internet, Anya?
I don't think so. Let me try to end screen sharing and start again.
Okay, I'll ask here also.
In any case, Anya, I sent you the direct Zoom link on your Slack. I think you probably have it on your email too, but I sent you on Slack as well, just in case. Okay, we see it.
Oh.
We now see it. It's not in the first slide, but we see it. So you just have to go to the first slide and it's.
Okay, I don't see it though. 1 second.
Yeah, we see a PDF like the talk ENSPN.
Right. Yeah. It's just that I don't see the.
You might want to retry it.
Yeah, go ahead.
To switch the share screen and then. Back again.
Okay, okay, I'll do it one more time.
Yeah,
Hopefully this
let's
time.
see that. Sometimes it works like magic.
Yeah, we see it again.
Okay, I don't see it, but actually I can just go by, hopefully I can just go to my
Or you can
screen.
try, do you want to leave and re-enter again in the Zoom session?
Maybe we can just...
you just don't see it in the Zoom, but you, yeah.
Okay, so, all right, let me go to the beginning. Oh, sorry.
Okay, so now we're on
everyone's
page
the
1.
title
Yeah.
page.
So,
okay,
yeah,
okay,
yeah.
great, great. And you can see my arrow, my
we
mouse?
can,
or?
yeah. Yeah.
Okay, okay, great.
At least I can, yes.
All right.
Okay, all right. So we'll
Yes,
start then.
Go ahead.
Okay, so
Okay.
Anya Katsevich from Quran in New York is going to tell us about the connection between log likelihood maximization and the method of moments in mixture of Gaussians with low signal to noise ratio. Anya, the stage is yours. Go ahead.
All right. Thanks, Afonso, and this is actually joint work with Afonso. So as you said, I'll be talking about the connection between the log likelihood and moments in low SNR Gaussian mixtures. So a Gaussian mixture model is a model for data drawn from several subpopulations, each of which is normally distributed. And we don't know which subpopulation each sample is drawn from. And this makes estimation of the mixture centers difficult, especially if the distance between the mixture centers is small relative to the noise sigma of each of the Gaussians. So we're going to be interested in the case where, in this case on the right, where the noise is larger. And we're going to consider the problem of estimating the mixture centers theta given observations yi. So in this talk, I'm first going to discuss the connection between two methods for parameter estimation in the orbit recovery model, which is a special kind of noisy GMM. And then I'm going to talk about our contribution, which is to generalize this connection to arbitrary noisy GMMs. So the standard approach for inference in Gaussian mixture models is expectation maximization, or EM. And so this is an iterative procedure where at each step you you assign probabilities that each of the samples came from each of the mixture components based on your current estimate of the mixture centers. And the probabilities are related to the distance between the observations and the mixture centers, like I'm showing in this picture. And so EM has a property that the log likelihood increases at each iteration, and this is going to be important for us later. And convergence guarantees do exist for EM, but primarily for the case of well-separated mixtures, and we're going to be interested in the case of poorly separated mixtures. So we're going to study what we call low SNR GMMs, which first of all have the property that each of the subpopulations has the same isotropic variance sigma. And for this kind of GMM, you can write the data as a sum of two terms. The first term, x star, which we call the signal, encodes the distribution of mixture centers. And then the second term, sigma z, is the noise around these mixture centers. And then we're going to define the SNR as the ratio of the distance between the farthest two centers and the noise sigma squared. And we're interested in the case of low SNR. So just as an example, if you have a uniform mixture of 3 Gaussians with centers theta j star, then x star, which encodes the mixture centers, is a random variable that takes the value theta j star with probability 1/3. So a special kind of low SNR GMM is the so-called orbit recovery model, which is a uniform mixture in which the mixture centers have the special property that they form an orbit under the action of a group G of orthogonal rotations. So in this picture, I'm showing a orbit recovery model where the group G is 5 orthogonal rotations in R2. And we're going to be interested in this case on the right where the noise is large. And as you can see, there's no hope of recovering the memberships of the samples to a specific subpopulation. But for the orbit recovery problem, the membership of the samples is sort of meaningless because the mixture centers, they're equivalent under this action of the group. And so we really only care about the means of the mixture rather than the memberships. And a motivating example of a low SNR orbit recovery model is data from cryogenic electron microscopy, or cryo-EM. So in cryo-EM, identical copies of a molecule are frozen in a sheet of ice in different orientations. And then we image the molecules and obtain 2D images of these molecules from the different viewing angles. So here I'm showing a schematic where I'm sort of forgetting that that the molecules are 3D and just assuming we started in 2D. So and cryo-EM is also very noisy typically. And so, of course, we don't actually have the orientations of the molecules. So we just have these noisy samples of the molecule and different orientations. So this is a good example of an orbit recovery model in low SNR. So there are 2 approaches for inference in low SNR orbit recovery models. First, since orbit recovery models are a kind of GMM, one option is EM. And EM has a special property that for orbit recovery models, it reduces to gradient descent on the negative log likelihood. And this is an important fact which will allow us to connect EM to another method called the method of moments, or MOM, which I'm going to talk about in a second. And a connection between these 2 moments was first observed in a paper by Sigris, studying cryo-EM data. And he noted that unusually, the estimation error scales like sigma to the cube when sigma is large for both of these methods. And since then, there have been several more insights into the connection between these methods, and they are based on essentially a Taylor expansion of the negative log likelihood in 1/sigma. And so I'll get to that later. But first, let me briefly go over the method of moments. So first, by moments, I mean the moments of the random variable given by the orbit under the group G of the signal theta. So we define the first moment as just the average of the G theta. And then the second moment is the average of G theta transpose, and so on. So the kth order moment is a kth order tensor. And so the algorithm works as follows. Given data yi, first, one can compute estimates tk hat of the true kth moments. And then one inverts the moments, by which I mean you find theta hat such that tk of theta hat equals your estimate of the true kth moment. And we assume that we can compute enough moments to uniquely determine theta hat from the moments. So it's rare that you can find an explicit expression for theta hat in terms of the moments. And so in lieu of this, a standard approach to find theta hat is to minimize this non-convex least squares objective function given by a weighted sum of the squared differences between the Lth moment of theta and the true Lth moment. And so it's going to be important to note that if the weights lambda are like arranged so that the first one is much bigger than the second one and so on, then minimization of this objective function will first prioritize matching the first moment to the true first moment. And then once it does, it will go on to matching the second moment to the true second moment, keeping the first one, the first moment equal to the true first moment. So we can think of this minimization as successively matching moments one after the other. So another development towards explaining the connection between the log likelihood and moments came in a paper that proved that MOM achieves the optimal rate of estimation for low SNR orbit recovery. And to prove it, the authors showed this upper and lower bound on the KL divergence, which is related to the negative log likelihood by a constant. And as you can see, these upper and lower bounds are similar to the objective function in moment inversion, where the weights lambda L are equal to sigma to the minus 2L, which has this property I was talking about where the first one is much bigger than the second, and so on, because remember that sigma is very large. And so this suggests a connection between moment matching and log likelihood optimization. But what we really care about is saying something about gradient-based likelihood optimizing algorithms such as EM. And for this, we want to know about the roughness of the landscape of KL. And of course, upper and lower bounds on the function can't tell us about the roughness of the landscape. So this suggests we need an expansion of the KL divergence itself. And so this was recently done in a paper by Fan, Sun, Wang, and Wu. So they derived the KL expansion for the orbit recovery model. And while it's not exactly this sum of square differences of moments, it still is of the form that we can draw the conclusion that optimizing the KL divergence reduces to solving this sequence of minimization problems where you minimize the difference between the Lth moments squared on the variety where the first L-1 moments match the true first L-1 moments. And so the implication of this is that analyzing EM or other gradient-based log likelihood optimization methods reduces to studying this landscape of moment matching problems. And this is also a sort of a challenging landscape to study. But in the case of the orbit recovery model, these moments TL of theta are invariant polynomials. And the authors of this paper leverage tools from algebraic geometry to analyze these moment matching landscapes. So our contribution is to generalize this KL expansion to any low SNR GMM. The only important condition is that the mixture centers do not go off to infinity, but they need not belong to an orbit of a group or have the same norm or belong to a discrete set or even be parameterized by a finite number of parameters. So any finite generic discrete mixture falls under our result, as do continuous mixtures, which have an infinite number of mixture components. And so in this very general setting, so what do we mean by KL divergence? So first of all, we assume that the true mixture centers have some distribution rho star, and we compare the distribution it induces on the mixture to the distribution induced by some other mixture center distribution rho. And by moments, we just mean the moments of rho. And so our result is similar to the orbit recovery KL expansion. And essentially, it says that if you have another distribution rho of mixture centers, which matches its first L-1 moments to the true distribution, then you can write the KL divergence as the square difference of Lth moments scaled by sigma to the minus 2L plus a remainder term, where this distance is the farthest distance between a mixture center in rho and a mixture center in rho star. And so this result has a similar implication that studying the log likelihood landscape of the KL divergence reduces to studying the landscape of these moment matching problems. And there are some important examples of low SNR GMMs, which are not of the orbit recovery type, but which do fall under our result. And one example is heterogeneous orbit recovery. And so, for example, like using the cryo-EM data, an example would be where you have several molecules, different molecules each of which are frozen in ice at different orientations, and you want to be able to recover both of those molecules. And while these moment matching landscapes are also like difficult to study, we hope that results about tensor decomposition can be used to analyze these moment matching landscapes and then transferred here to say things about the log likelihood landscape. And just to demonstrate our result for just a uniform mixture of 3 components, this is showing the EM trajectory, and basically it's showing that first the estimates reach this plane where the first moments match, and then it moves along the plane towards this circle where the first 2 moments match. And once it reaches it, it moves along it towards the true mixture centers. All right, thank you very much, and I welcome your questions.
Thank you so much, Anya. Okay, maybe we have a couple minutes for maybe a quick question, maybe 2.
Hi. Hi.
Oh, João, go ahead.
Yeah, very interesting talk. I'm very interested in this because this was a big topic of my PhD thesis, actually. And in particular, can you go back to slide 17? Yeah, so my question is, in this theory that you developed, do you use more than the KL, like, is the main recipe this expression for the KL divergence? Or does the noise being Gaussian is an important part as well? Or let me say what I'm thinking. So in my thesis, I actually have an expression like this that works for any kind of noise. It doesn't need to be Gaussian. I haven't published it yet, but it's there in the thesis. So I was wondering, do you think it's able to generalize for any kind of noise distribution rather than just Gaussian if they have a similar KL expression?
That's a very interesting question. Yeah, our like Taylor expansion pretty significantly use the Gaussian form of the noise. Yeah, so I think like it was complicated because the fact that the mixture centers don't have the same norm like really changes the proof compared to the proof for the orbit recovery model. And so like in lieu of that, we had to rely on at least like the structure of the Gaussian PDF. Yeah, I've thought about it and I don't actually know. Maybe at least densities in the exponential family would be important.
So actually, let's say you have some expression like that. Do you think you can actually get a similar theorem using just a Taylor expansion, or?
I think it's possible, but yeah, I think it's potentially, but yeah, I don't really know how to do the Taylor expansion for a non-Gaussian. Yeah, but that is very interesting.
I'll talk with you offline.
Okay.
Actually, I kind of have an idea. It's different, but and there's some thing in the middle that you don't actually know how to calculate. But yeah, I'll send you this offline, I think. So.
Okay, yeah, that would be great. Thanks.
Okay, excellent. All right, so we'll. I think we need to move on to the next talk. So it's actually João, right? If I have my schedule correctly. Yeah.
Yeah.
So from a very related topic.
Yeah.
These 2 talks are quite related.
Yes, and
if you can
I
share
share my screen? Yeah.
You should be able to.
Okay.
We can see it, but we see the graph. Okay, now we see the.
Yeah.
Yeah. Okay. So João Moraes Pereira is coming to us from U Texas in Austin, and is going to tell us about the method of moments and implicit symmetric tensor decomposition. João, take it away.
Hi everyone. Thank you for the. It's an honor as a Portuguese researcher to be talking here at Encontro Nacional de SPM 2021. So as Afonso told you, I'm going to talk about implicit symmetric tensor decomposition and using method of moments. And actually, it's very interesting that Anya talked about what she talked about because, and I was not thinking about mentioning it, but I'm going to present an algorithm for implicit symmetric tensor decomposition. And one thing that one application that we're thinking about it, and you can actually use it for, is to use the method of moments and higher order moments to do to decompose Gaussian mixture models. And actually, it works very well. I don't have plots right now for it, but so it's interesting that things connect so well. But let me just go ahead and start explaining what we. So we Annie already talked a little bit about method of moments, and so when we think about method of moments, sometimes we only think about. So we think about one-dimensional distributions. In that problem, the method of moments is well known, or we use first and second order moments to decompose. Like first order moment is the average of the data, and then the second order moment is the covariance. And so we analyze these two, and then we do PCA on the data to see how it's distributed. And this is also done a lot of times. And then there's this case where we actually know something about the data, and we can use the higher order moments and invert them directly to get the parameters that we are interested about. But my question is, why is there not some kind of a PCA algorithm for higher order PCA that uses the third order moment and the fourth order moment tensor and just decomposes the data and gets more information than just the covariance? There's some reasons why we don't do this. Okay, I went to the wrong direction. Okay, so one of them is that actually computing tensor decomposition is NPR. So some of the things that we can do with matrices and that are very well known, computed eigenvalues, getting a lot of decomposition is efficient. But then when we go to tensors, higher order tensors of order 3, 4, then the thing gets to be harder. And then another reason, which is very important in this world of data, that tensors are very big. So let's imagine our data is images with 1,000 pixels. Then covariance of these images would be, the covariance matrix would be 1,000 by 1,000. So it would be 1,000,000 entries, which is something that computers can store and can deal with. But then if we start going to tensors, which have 10 to the 9 entries and 10 to the 12, if it's a tensor of order 4, then you can't even store it on the computer, much less manipulate it. And so what can you do to use tensors without actually using them? So, and what I'm going to talk about is an algorithm that decomposes low-rank tensors without explicitly forming them. So just using the data, and you never form the tensor, but you're able to actually decompose the tensor. I'm going to explain how that's going to go. An important part here is that I'm decomposing low-rank tensors. So although the computing tensor decomposition of tensors is NP-hard, if the tensors are low rank, and by low rank, I mean the rank scales as the square root of the number of entries, because in general, the rank of tensors is much higher than that. But if the rank scales as the square root of the number of entries of the tensor, it is believed that there are efficient algorithms that can do it. And I'm going to present an algorithm that does that. And so for the people that are not used to tensors, I'll just explain what they are. A tensor is just a higher order array of numbers. So a matrix is a 2D table of numbers. Then a 3D, a tensor of order 3 is just you put another dimension, you have a 3-dimensional table of numbers. That's a 3D tensor of order 3, and then you can go tensor of order 4 and so forth. And the higher order moments moments of higher order moments are symmetric tensors. And what is a symmetric tensor? Is a tensor where all dimensions are the same, and then if you permute any dimension, the tensor remains the same. Is invariant to permutations. And so I'm going to call the order of tensors the number of dimensions. And because all the dimensions are equal, because if you permute them, the dimensions need to be equal when you permute them, I'm just going to call that the dimension. Because all dimensions are equal, I'm just going to call that dimension. So the tensor, I'll be talking about symmetric tensors, which have some order and some dimension. And if you have a symmetric tensor, you can think about rank 1 tensors. So if you have a vector, you can form a rank 1 matrix by taking out the product of the vector with itself, right? And then you have a rank 1 matrix. And now to get a rank 1 tensor, you just do the outer part in the other direction to get the third order rank 1 tensor. The fourth order, you keep doing this. And so the question we might ask is there a decomposition that writes the tensors as a linear combination of rank 1 tensors? The answer is yes, there is one. It's called symmetric tensor rank decomposition, or it's also very well known as CP decomposition or CAN decomp. And it's in general unique for rank deficient tensors. And it is believed that for long rank tensors, it's possible to compute, but in general, it's NPR to compute. And so I'm going to provide I'm going to describe an algorithm for decomposing tensors. Right now, we'll be still thinking about tensors, and we'll still form tensors. In the end, I'll explain how we can go ahead and do this without actually forming the tensors. And funnily enough, the algorithm that I'm going to describe, we gave a name to it, so it's more catchy. And the name is SPM, which I thought it's funny because I'm talking about SPM on the SPM convention. So let's assume the algorithm works best for even order tensors. So let's think tensors of order 4. It's a good idea to think about tensors of order 4. And so how do this algorithm works? So we can think of tensor decomposition as some special kind of matrix decomposition. So take your tensor, let's say it's dimension 4, so it's d by d by d by d, and flatten it into a matrix which is d squared by d squared. So you take 2 dimensions, you make that 1 dimension, and take 2 dimensions, the other 2, and you make that 1 dimension. And now you have a d squared by d squared matrix. And you notice that it actually can be, the tensor decomposition is equivalent to this factorization, where each column is a rank 1 vector, or like a flattened rank 1 matrix, or a flattened rank 1 tensor if n is bigger than 2. And then it's a diagonal matrix with the coefficients. And by the way, so for the decomposition, I'm going to call the AIs the tensor components and lambda i's the tensor coefficients. And so there's this decomposition of the tensor rank decomposition is equivalent to this decomposition, this matrix decomposition. And in particular, one thing we already see is that if this matrix here is full rank, then the column span of the matrix, the flattening of T is going to be the same as the span of all the rank 1 AIs in the span of all the rank n, the outer product of the tensor components, right? And so when the first step of the SPM algorithm is to obtain an orthonormal basis of this span, right? Which we can do just by doing the eigen decomposition of this flattening of the matrix. So, and we're going to get this V, the columns of V live in a space of tensors of rank n, and there are orthonormal bases in this space for the tensors of rank n of spanned by the coefficients of the tensor. And so in particular, one thing we also get from this is that the rank of the flattening is equal to the rank of the tensor. So we get the rank automatically. We don't have to guess the rank. We don't have to start with a smaller rank and then increase if it's not good enough. We starting point, we already get the rank. And now what we're going to do is we're going to peel off each component, AI, get the corresponding lambda I, and then take it off out of the tensor. And we do this and we'll get all of them. And that's how the algorithm is going to work. And so I'm going to explain how we obtain rank 1 points in this subspace in the next slide. But for now, let's imagine we can get them. The question is, okay, we have a span of rank 1 points, right? Let's say we have a span of rank 1 matrices. Does this span create more rank 1 matrices? Is there more rank 1 matrices than the ones that are spanning that space? These AIs that we know that are spanning the space? And the answer is that for generic AIs, so if you sample them at random, for instance, then they're not going to be more rank 1s. And so if you find rank 1 point, a rank 1 vector in this span, we know that's one of the tensor components. And so let's imagine I have some way of finding these rank 1 points. We find one. How do we find the corresponding lambda I? And so the idea is that we can, if we subtract lambda I times the flattening of AI to the power of 2n, this thing is going to make the matrix to drop rank. And so we can figure out what lambda I is by trying to make this difference drop rank by 1. This is called Wedderburn rank reduction. And actually the formula for lambda I is given by this. So it's this component to the power of n transpose times the pseudo inverse of this flattening of t times the vectorized version of AI to the power of n. And now that we have lambda I and AI, we can update V and D such that, and update the eigenvector decomposition of the flattening of t without the lambda I and the AI. And now this is a flattening of a tensor of rank r-1 without the AI and lambda I there. And now we can keep doing this until we find all the lambda I's and all the AI's. And this is how it works. And so right now, finding an orthonormal basis is guaranteed to work. Deflation is also pretty much okay. Now the question is, how do we find rank 1 points in A? So it turns out if you want to find rank 1 matrices in a subspace of matrices, it's NPR. But we have an idea that works well in practice, and the idea is simple. It's just you take your vector x, you take its outer power, and then you project it to A, and you see the norm of that, and now you do gradient descent on x. And so this value of f, and by the way, you guarantee that x has norm 1, because it doesn't really matter if you find AI, you just need a AI up to scale, so you can assume that AI has norm 1. And so you can notice that this function is going to be bounded between 0 and 1. And then it's 1 only if x to the power of n is on the subspace A. So it means that x is one of the rank 1 points in A, and in particular that it's one of the tensor components. So the tensor components are exactly the global maximum of the objective. And now the question is, first, do a gradient descent converge to a local maximum? And we know that it might not converge to a local maximum, but it's going to converge to a second order critical point. By second order critical point, we mean a point which the gradient is 0 and the Hessian is negative semi-definite. So it might be a saddle point, but it's like one of those saddle points which is barely a saddle point, but it can still be a saddle point. And now the question is, is there bad local maximum? And that's something that we studied for random tensors, and actually we just published a paper on that this June. We submitted to NeurIPS. We're still polishing up the archive version, and we're going to submit it to archive soon. But the idea is that for random tensors, then all the bad local maxima are very, very small. The function value is very, very small. And so if you sample at random and you do a few iterations of the power method, you know that you're already going to fall off you're already going to be above that level set. And then you know that you're going to get a global maximum. So one of the tensor components. And not only that, but actually SPM is also robust to noise for random tensors. So if you perturb this, so if you have a tensor, you actually, the tensor is only approximately low rank, then you still, the global maxima are only going to be perturbed by a little bit. And you can actually quantize this in terms of the perturbation of the subspace. And so this is in a paper that will be available soon in the archive. And so to finish with SPM, and let's remember that we're still talking about tensors, with explicitly formed tensors, this is already a very fast algorithm. So on average, SPM is 20 times faster than the state-of-the-art TensorLab, which is basically trying to do alternate minimization. And this is much faster than anything we've found. We challenge people to try to find something that is faster, but SPM is very, very fast. And as an example, a tensor with 1 million entries, 10 to the power of 6, and rank 150 takes only half a second to decompose. So you click enter, you blink, and then it's done. So this is already a very fast algorithm. And then a question, and this was proposed by a collaborator of us, that she saw our talk and she wondered, wait, can you do this with implicit tensor decomposition? What is the idea of the implicit tensor decomposition? So let's suppose T is a moment tensor. So what is a moment tensor? You have samples WL, and now you take their outer product and then you average them, right? And so can you decompose this tensor without actually forming it? And you might wonder, how do you even do that? So it turns out, so you can calculate dot products of these tensors with rank 1 tensors without explicitly forming it. Why? Because this dot product is actually going to be the end power of the dot product of each sample with alpha. And now you can, while this is the dot product between tensors, this actually can be calculated dot product between the samples and your vector alpha. And it's much faster to calculate than actually computing the old tensor. The problem is that you always need the samples. But you can actually use this to build this idea to implement SPM to decompose a tensor without explicitly forming it. And the computation costs are much smaller than what you think. In particular, they don't depend on almost anything. So the extract subspace doesn't depend on n at all. And it takes time, which is linear on the number of samples, and then scales with the square of the rank of the tensor. And then the power method, so these are the 2 iterations of the method. The power method is going to scale linear again with the number of samples, and then square with the rank, and then there's the dimension, and n appears there, but n is always very small. So you can imagine that this is not going to matter on n at all. And then the deflation step also has a similar scaling. And let's see how it works in practice. So I have here an example of how implicit SPM works. Let's say we have a tensor of order 6. And then the dimension of the tensor is 500. And the rank is 100. And then the number of data points is 2500. And then the noise of each entry is 1%. So this is a huge tensor. If you actually calculated and estimated this tensor, which you don't, but imagine you did, you'd need 125 petabytes of memory. So petabytes is 1,000 terabytes, which is 1,000,000 gigabytes. So you would need 125 million gigabytes of memory to start this tensor. The good thing is we don't need to calculate the tensor, and actually the implicit SPM takes 3.5 seconds to decompose this tensor. And by the way, this could be, so I come back to Anya's talk, this could be a Gaussian mixture model where you can actually, I think this was actually a Gaussian mixture model, the model behind this. So think a Gaussian mixture model where you have 100 centers, the dimension of each point is, the dimension of the centers is 500, and then the number of points per center is 25. Yes, 25. And then you calculate the centers with the error is this one. I'll just talk briefly that we can also do something else with the SPM, which is really interesting. SPM can also be used to fit a union of linear subspaces. So imagine our data, it's a little bit like PCA, but PCA is just a subspace. And now think of a union of linear subspaces. So this is a non-convex problem, ideally non-convex, but this is still, or SPM is able to solve this problem. And it computes a different kind of generalized tensor decomposition that is able to actually recover these subspaces. And implicit SPM can also be used for that particular application. And that's very exciting because you can have very nice potential applications. And I conclude by showing the references, and in particular, thanking my collaborators. My main collaborator on this is Joe Khalil, and then we also worked with Timo Klock and Tamara Kolda on these works.
Thanks so much, Ron. Okay, so maybe we have, we're running a little behind, but we have time for a quick question.
I have a question.
Go ahead, Chris.
So I don't know how much of a relationship there is, but this business of flattening a tensor into a matrix which is as square as possible, which works out, as you say, especially nicely when the order is even, also shows up in these sum of squares algorithms and so on for noisy tensor decomposition. So I was just wondering if, you know, what can you do in the presence of more noise?
What do you mean? So the idea is you really want to get to a matrix which is more. That's why even is good, because you want all the dimensions to be more or less the same. So so you have a higher dimensional subspace and you can go to higher ranks. So I didn't understand your question about. So yeah, we do have that, and SPM also works very well for noisy tensors. No, not only it doesn't need to be exact low rank; it can be approximate. In that regard, we have so when you compute the eigenvector decomposition, you're going to figure out what is the rank, and by doing that, you have to figure out the cutoff on the eigenvalues, such that above these eigenvalues, you keep it, below you cut it out. And it's kind of a spec model thing that you have to think about, and which is not really very developed for tensors and needs to be more developed. Did I answer your question?
We can talk more offline.
Okay.
Yes, thanks.
Thanks. Yeah, I also have some questions, but I'll ask you offline maybe so that we can go to the next talk. But so, okay, maybe let me ask a very quick one because I'm quite curious. So this goes up to, you expect to be able to handle rank like dimension to the order over 2, something like this? So yes, that the subspaces are, you know, the dimensions work out when you do half of the dimension? That's what exactly. That's the intuition I should have? Yeah, so the rank is about the square root of number, so the dimension of the subspace. Okay. Okay, very cool. Okay, so we'll go for the last talk of the day, and I think the last talk of the whole meeting. Right, so we have now, so Chris Moore is going to tell us about fascinating connections between computation and physics and networks. We're a bit delayed, so I want to introduce Chris for very long. Let me just say, if you haven't read his book on the nature of computation, you should get it, and you should, if you're in Portugal, you should go enjoy the nice weather in the beach and read this book.
Can you see my
Chris,
slides?
The stage is all yours.
Okay, and you can see my slides okay?
Yeah.
Okay.
That's great.
So thank you very much for inviting me. I really wish that I was in Lisbon having some pastel de blanc and then riding the funicular up to Bayreuth for some fado, but maybe next year. So I've had the pleasure of having lots of different collaborators who operate on different points on the spectrum from, well, I guess actually the two-dimensional landscape between physics, computer science, and mathematics. Some are mathematically rigorous people, others are physicists who do calculations and make conjectures, and there's been a wonderful interplay between these different points. So I want to talk about some of the work that's come out of this analogy between statistical inference and statistical physics. And, the basics of this analogy, which you may already know, are that if you have some generative model and you're doing Bayesian inference, then if you write down the log likelihood as a so-called energy, what physicists call a Hamiltonian, then the posterior distribution is exactly what physicists would call an equilibrium distribution, a Boltzmann or Gibbs distribution. And this analogy, I think, is pretty well known, but there's lots of additional import-export we can do across this bridge of ideas from physics, especially the branch of physics called spin glass theory and the theory of disordered materials, and things that you've heard of, like the replica method and all this fun stuff, much of which has been quite challenging to make mathematically rigorous. So, the overarching question is, we have some noisy data. We believe we have a good model, both of how the patterns in this data were generated and a good model of the noise in the data. And given that model, we want to infer those patterns or detect if they exist. And just as in physics, we have various phase transitions where water melts when you make it hot enough, and magnets cease to be magnetized if you make them hot enough. There's often some phase transition where at a critical amount of noise, when you fall below some signal-to-noise ratio, for instance, because there's too much noise, suddenly it becomes impossible to find these patterns. And so we want to do several things. We want to locate these transitions. We want algorithms which are optimal in the sense that they succeed all the way up to these transitions. And in fact, we'll find that there are two different types of barriers that we might encounter. One is information theoretic, where there's so much noise that the information is literally not there in the data to find the pattern, no matter how much computational power you have. But there might be other barriers where the problem is still information theoretically possible to solve, but it becomes computationally infeasible. So, where, as we heard earlier in the session, alluded to, we have some kind of rough landscape with many local optima and we get stuck. And, so if we had all the time in the world, we could solve the inference problem. But if we're limited to polynomial time and efficient algorithms, then it's conjectured that we can't. Okay, good. So here is the classic Ising model. It's a model of magnetism, and in which neighboring atoms want to line up with each other in a block of iron, say. And as when the temperature is very low, that almost all of them line up. They're all pointing up or they're all pointing down, all their little magnetic fields. And so the block of iron as a whole is strongly magnetized. And it was discovered first by Pierre Curie that when you might have heard of him, he was married to Marie. So when you raise the temperature past a certain point, quite suddenly in the laboratory, the block of iron loses its ability to hold a magnetic field. And so what it looks like microscopically is that below this transition temperature, there's a clear majority of the atoms which are aligned with kind of small and temporary islands of the minority. But above this transition temperature, while there are still small clumps of atoms that are lined up together, at a large scale, it looks like white noise. And in informational terms, you can think of the atoms trying to communicate with each other. But over a noisy channel, I'm trying to convince you, if you will, to have your field pointed up. And I have some influence over my neighbors, but to get that effect far away from me in the block of iron, although there are many different paths by which the information could travel, there's also noise because even my neighbor might be probabilistically not the same alignment as myself. And so there's a kind of competition here between the combinatorics, or the entropy of the number of paths, and the ability for each individual path to communicate. And so this energy entropy trade-off from the physical point of view turns out to create this phase transition. So what I want you to imagine now in a data science or machine learning context is a similar transition in, say, a clustering problem, where now instead of heat, we have noise. And this looks a bit like some figures we saw earlier in the session. And so here the measure of noise might be the width of these clusters compared to the separation between them. And there might be a sudden transition below which you can reliably label most of the points according to which cluster they come from, but above which you might not be able to do any better than chance and asymptotically. And by the way, this is in a high dimensional context. So where these points, where I have n points in, say, 0.1 n dimensions. And so the ratio of the number of points to the number of dimensions they live in is only a constant. So this is in this so-called high dimensional statistics regime. And that's where these transitions typically live. So good. Now, I'm going to focus on the rather popular community detection in networks. So this is a kind of typical picture from Talks About Networks. This is from a 2004 paper where someone collected blogs that were, roughly speaking, on the left or right of the political spectrum, in this case in the United States. And since human beings have this annoying habit of only talking to people they agree with, these blogs are strongly connected within these two communities and only sparsely connected between them. So a favorite pastime in network science is I give you just the adjacency matrix of this graph, and I challenge you to find the two communities. So I hide from you all the information about the content of these blogs and things like that, and we just try to separate this graph topologically. Now, for a lot of real networks like this one, the structure is so strong that almost any algorithm works. And people argue about, oh, I got 97% accuracy and you got only 96% accuracy, and haha, I win. But you know, if the structure is really strong, then all sorts of algorithms will work very well. But I got curious about this a while ago because many of the sort of popular software packages that you can grab off the shelf and run on your network don't give you much sense of, are they confident about the way they labeled the nodes? Are there alternate ways to label the nodes? They just sort of hand you a labeling, which, especially when it's put on your screen in a visually attractive way, of course, is very seductive. So here is a network where I have separated it into two groups, where only 11% of the edges cross between the two groups, and the other 89% are all within groups. So you might think, oh, good, this is a very convincing division of this network into two communities. On the other hand, here is another such division with also only 11% of the same graph. And you can see from the colors that is completely uncorrelated from the first division. So, well, this should give us pause, right? I mean, if we're actually trying to do some social science here, which division should we believe, if either? Well, it happens to be that this is all a cheat, a hoax, because what I generated here was a random 3 regular graph where everybody has 3 neighbors, but they're wired up randomly to each other. So there actually are no real communities here. And in fact, it turns out that even random 3 regular graphs, out of the roughly 2 to the n ways to divide them into 2 groups, or n choose n over 2, there are indeed many ways to divide them so that only 11% of the edges cross from one group to the other. And so, well, this suggests that what's really happening here is some kind of overfitting. So, you know, both we and our algorithms are very fond of finding patterns that are not there. You know, the old saying of finding black cats in dark rooms, even when they are not there. And of course, it's also very tempting to fit, in many scientific communities, it's tempting to use fancy models rather than, you know, rather than the model best justified by the data. So, you know, I show my students, here's a set of points, we can fit them perfectly with this higher order polynomial, but what we should be doing is fitting them with a low order polynomial more noisily, and that actually does a better job at predicting the data that we haven't seen. So anyway, we want to fit, in some sense, the ground truth, not the noise or the randomness. And so what we saw before was that sometimes these communities can be fictional. So this has made a lot of people want to solve this problem in a more principled way as a statistical inference problem. So there are a number of ways to do that. And I'm going to skip over this slide because of time, but I also just I'm almost going to skip over the slide. Ideologically, right, we often view inference as an optimization problem. For instance, find the maximum likelihood fit of a model to data. Well, if the landscape of fits looks like Mount Fuji here, that's a good idea because it's really dominated by the peak. And any model which is pretty good is also close to that maximum likelihood model, the highest point on the peak. But if the landscape looks more like this, well, first of all, optimization is hard because there are many local optima. But secondly, even if you could solve the optimization problem, the answer might be misleading. In some sense, you really want to understand the entire landscape. And if what you have is many, many peaks of roughly the same height, maybe what's going on is that the kind of pattern you're looking for isn't even really there. And so that red and blue figure I showed you a few slides ago has many good-looking divisions into communities corresponding to lots of different peaks, but actually there are no real communities at all. So I'm just trying to push the idea that whenever we can, we should try to understand the entire landscape of fits to our model rather than finding the single best one. Okay, now, so I'm going to look at a particular model. It was originally invented in sociology, but it's been reinvented many times by people who study random graphs, people in computer science, people in physics. It's called the stochastic block model. And it's a model which generates random graphs which have community structure. So if you give me your graph, one way to find communities is to try to fit this model to your graph. So I have k types of nodes. They're the communities, the labels, whatever you want to call them. In this model, k is a constant, and I will assume that k is known. The model selection question of how large k should be is interesting and important. And then there's some k by k matrix of connection probabilities, which tells you the probability that a given pair of vertices in this group and in that group have an edge between them. Now, I'm going to work in the sparse regime, which is also in some sense here the high dimensional regime. So I'm going to assume that the average degree of this graph as n increases, is only a constant. And so the probability that any particular pair of nodes is connected is order 1 over n. This is where these phase transitions live. If it's quite dense, then this problem is intuitively more simple. And then a popular special case, scaled by 1 over n, is to say that you have some typical number of neighbors in your own group on the diagonal of this matrix, and then for each group for each of the other groups, you have some other smaller typical number of neighbors. Actually, that should be scaled by k, but anyway, that's the idea. And then what we would call a ferromagnetic thing, where you're more likely to be connected to people like you, would be where those diagonal elements are higher than the off-diagonal ones. All right, so we can write down the likelihood that this generative model would produce your graph given a set of labels very easily. I just told you what it is. It's just the product over all the edges that are there, of the probability they're there, and the probability over all those that aren't, of the probability that they aren't. But of course, what you want to do is invert this and try to find the probability, the posterior, the probability of these labels given the graph that you've observed. So the idea here is to use this physics analogy that's going to be like a state drawn from this Gibbs distribution where the energy is just minus the log of this probability, which changes these products into sums. And this now looks a lot like the Ising model of magnetism, where neighboring nodes have some energy depending on whether they have the same magnetic orientation, which now becomes which group they belong to. There's also this weaker interaction between non-neighbors, which is kind of interesting. There are many more of those interactions, but if p is order 1 over n, then log of 1 minus p is also order 1 over n. So you have strong interactions between the neighbors and weak interactions between the non-neighbors. What those weak interactions do is they prevent the model from saying, hey, I can make the likelihood big by putting everyone in one huge group, right? So the non-edges say, well, wait a second, why aren't these connected to those? It encourages to have multiple groups that are not typically connected to each other. All right, so now this is a physical model, and now we can try to import these ideas from physics and see what we learn from that. Okay, so what I like to do with these models, and lots of other people do too, especially what you might call the European spin glass axis of statistical physics, is something called the cavity method, which is essentially the same as belief propagation. And it's related to replica symmetry, but for me personally, it is much, much easier to understand. And so what we have is messages sent from node to neighboring node. And, I'm a node, Afonso is a node. I send Afonso an estimate of the probability, my marginal distribution, the probability that I belong to this group or that group or that group. But with this important twist, which is that when I calculate my message that I'm going to send to Afonso, I base it on the messages I receive from my neighbors other than him. And when I talk to them, I take his message into account, but not the message they sent to me. So this is an interesting scheme. It's a little bit more advanced than what people call naive mean field, where I take everybody's incoming messages to me, calculate my marginal, and broadcast that back out to everyone else. This little twist of not using Afonso's message to me when I calculate my message to him, I don't have time to tell you why that's a good idea. It's a sort of more, if you will, you can view it as a fancy variational method, but the intuition is that it avoids a kind of silly echo chamber between him and me, where he sends me something, I take it, I sort of amplify it and send it back to him, and it bounces back and forth, like a lot of opinions seem to do in our society right now. Instead, it brings fresh information into our conversation from the rest of the network. So there you go. That's the analogy. So this idea produces a kind of update equation, which is basically just a local application of Bayes' rule. And the idea is we start with some random messages and then do this update until we reach a fixed point. Well, this may or may not work, right? We may fail to converge. We may converge to a fixed point, which is actually a terrible estimate of the true marginals. Okay, but often it does work, and often it does work quickly. So it also yields this interesting quantity called the beta free energy, named after Hans Bethe, which is a kind of estimate of the true free energy, or if you will, an estimate of the total log likelihood that this model would produce your data if you sum over all possible labelings of the nodes, all possible divisions into different communities. So it's a lovely idea, and a lot of effort has been put into understanding when it works rigorously and when that beta free energy is a rigorous bound, or better yet, an asymptotically a good estimate of the marginals. So here is what these update equations look like. I don't want to take too much time. You know, I'm just sort of kind of throwing this at you in a way that I always tell people not to do in talks. I don't really mean for you to parse it, except there is this product of a sum, and that is tantamount to assuming that my neighbors are independent of each other, conditioned on my own state. Or to put it differently, that they interact with each other only through me, right? My friends are correlated only because they're both friends of mine. Well, of course, this is quite false in many settings. I mean, lots of real networks have lots of short loops. My friends are probably also friends of each other and interact directly. So this is a source of error in belief propagation. And that's why belief propagation is exact only on trees. And so the question then is on, you know, when is it asymptotically not too bad? And there's a lot of settings where we know that. So for instance, in sparse random graphs, there are short loops, but they're rather rare. Most loops are kind of long. And if there's some kind of correlation decay as we go around these loops, then by the time my two friends talk to each other along a path that doesn't go direct through me, hopefully that information hasn't made much of a difference. There are also interesting cases of dense graphs where the interactions are all weak, where again, asymptotically, this turns out to work pretty well. Anyway, so some time ago, some friends of mine and I, who were physicists, ran belief propagation experimentally on large random graphs. And we also did an analytic but non-rigorous calculation of how well belief propagation succeeds on graphs that are generated by the stochastic block model. Okay, so on those random graphs, how well does this recover the true underlying labels of the nodes? And what we found, and what they expected to find from other work that they had done on things like graph coloring, they predicted the location of a phase transition where, when a ratio between how often you connect to people outside your group versus inside your group, when that ratio is small enough and the community structure is strong, well, as you might imagine, belief propagation does a good job. But above a certain critical value of that ratio, it just arrives at a useless fixed point where everybody says to everybody else, I'm equally likely to belong to every group. And then everybody does the math and say, oh, me too. I'm also equally likely to belong to every group. So if belief propagation falls into this uninformative fixed point, this uniform fixed point, then in some sense it does no better than coin flips, right? So what we found was that above this transition, this fixed point becomes dynamically stable. It sucks in all of the initial guesses of the messages. So based on this, in a physics paper, we conjectured that in fact, when I thought this was kind of gutsy, but my co-authors twisted my arm, that not only does belief propagation fail in this regime, but all algorithms fail, that there's nothing you can do, even with exponential computation time. And then a few years later, this was proved by Massel, Niemann, and Sly, and then also a positive result was shown by Massoulier. And at this point, we know a lot more about this system, at least in the case of two groups, that indeed it's information theoretically impossible to find the labeling better than chance above this point, or even distinguish these random graphs generated by the block model from completely flat, featureless random graphs that have no community structure at all, by which I'm referring, for the aficionados, to Erdős-Rényi random graphs. Okay, so above this point, we can't find the communities. We can't even tell if communities are really there. So I'm sorry about the axis flip, but there's a nice, C here is the overall average degree, the overall density of the random graph. Lambda is a measure of the strength of the community structure. It's the second eigenvalue of a little transition matrix, what happens to your probability distribution of which group you belong to based on mine when we traverse a single edge from you to me. So it's another model of the strength of the community structure. So we now know that when this thing, the overall average degree, C, times the second eigenvalue, lambda squared, exceeds 1, then for two groups, there are simple algorithms, fast algorithms, that do quite well, including both belief propagation and a variant of spectral algorithms, which I will tell you about in my last 5 minutes. Below this point, it's information theoretically impossible. So for two groups, rigorously, and for three groups, conjecturally, this problem is either easy or impossible, okay? There are efficient algorithms or no algorithms at all. Interestingly enough, by the way, there's this beautiful connection to this phylogenetic reconstruction problem where there is an ancestor rabbit. Rabbits reproduce asexually, as you know, and each time a rabbit has a child, with probability lambda, the child inherits the parent's color. With probability 1 minus lambda, the child's color is uniformly random. Okay, we do this many generations, and then we ask from that future population, can we infer better than chance the ancestor of the original, the color of the original rabbit? Well, this is a lovely problem in discrete probability, and it has this same threshold that when if C is the average number of children and lambda is that probability of inheritance, when C lambda squared is bigger than 1, you can do this inference problem for two colors. And when it's less than 1, there's nothing you can do. And so Massel, Niemann, and Sly proved this impossibility result by relating the community detection problem to this phylogeny problem. So the metaphor is that, let's say that you're trying to figure out my label, my neighbors are my children, their neighbors are my grandchildren. We go out many generations, and then you're going to be generous and tell me the true labels of all the nodes far away from me. Well, if even with that additional information, you can't figure out my color, well, then clearly you're not going to be able to do that without that information. So that's how their impossibility result works, roughly speaking. So that's great. And by the way, again, even for 3 colors of rabbit or 3 different communities in a network, we still don't know quite what's going on. So here we don't have not all the physics has been made rigorous. But then bizarrely enough, you might think, oh, 2 colors, 3 colors. Once we hit 4 or 5 colors or more, a new phenomenon appears. And this graph is kind of busy. I'm going to skip over it because we're running low on time. But here, what's going on? Now there is an easy regime, an impossible regime, and in between a regime which we believe is possible information theoretically, but computationally hard. How could that happen? Well, window glass is made out of silicon dioxide, and it would really like to be in a perfectly crystalline state. That would be its lowest energy state. But when you melt glass and cool it down, it never finds that state. It never reaches a true sample from its equilibrium distribution. It gets stuck in an amorphous state, which microscopically looks more like a liquid than a crystal. And it will stay there until the stars burn out. It is separated from where it wants to be, its lowest energy, highest likelihood state, by an energy barrier, which will take exponential time to cross. In the same way, you can imagine a problem in data science or machine learning, where there is a good solution, say a good clustering of your data points into two groups, and if I showed it to you, or if you happen to find it, you would know that it's good, okay? You would know that it's a high likelihood state. But a typical algorithm that's doing some kind of Monte Carlo or belief propagation or whatever will get stuck for exponential time in this amorphous state where it has does no better than chance. So the idea is that if you had exponential time, you would eventually cross this barrier, or if you could rerun your algorithm from an exponential number of different initial states, you would get lucky and start in this narrow basin and find that state. But with efficient algorithms, there's nothing you can do. So this is basically the intuition behind this conjecture. So we now have a situation that looks like this, which has been made partly rigorous, where there's still an easy regime up here, there's still an impossible regime down there, and then there's this regime in between where we conjecture it's computationally hard. Now, and here I'm going to kind of skip to the end, to the spectral thing, which I just want to show you. As you know, we do not yet know that P and NP are different, right? So we have no hope of actually proving that this regime requires exponential time, because we can't really prove that anything hardly requires exponential time. But we could hope to prove that many of our favorite algorithms take exponential time or succeed with exponentially small probabilities, so we would have to run them an exponential number of times. And there's an increasing number of rigorous results of this kind, showing that all sorts of families of message passing algorithms and spectral algorithms and algorithms involving something called the sum of squares hierarchy, which is of a lot of interest now in computer science, where you use algebraic methods. You treat the system as a system of polynomials, and you try to show that there's no feasible solution. There's a lot of results now showing that the algorithms we know about fail. So a kind of, if you will, I mean, some people find this convincing and others don't, but people like me think that there's an increasing amount of evidence now that this middle regime is genuinely hard. So I'm going to skip over some extensions of this work where I tell you some of the labels for free. There's a phase transition there where if you know enough labels, then that kind of percolates as an epidemic, and then you do quite well. There are questions about what if you don't have the parameters right? Maybe you're overfitting or underfitting because you don't know how many communities there are, or you don't know how strong the community structure is. There are papers you can write about that as well. You can divide communities into sub-communities and then sub-sub-communities, and trying to get a hierarchical picture. This is that blog network I mentioned earlier. I just want to end with, in my -1 minute, because I wanted to stick to 30 minutes here so we'd have time for questions. So you probably know about spectral clustering, very popular. You want to divide your graph into two pieces. Well, what do? You take a linear operator associated with that graph. It's adjacency matrix, it's Laplacian, it's normalized Laplacian, whatever. There are lots of them. Then, if there are two groups, well, the second eigenvector will typically be positive on one group and negative on the other group. And this would be, if you will, the last deviation from uniformity to disappear. If, for instance, heat were flowing from node to node, or probability was flowing from node to node according to a random walk. So this is a popular way of doing this. When does this work on the block model? Well, a number of people have looked at using random matrix theory. You can look at the noise in the graph. The randomness in the graph produces a spectrum very much like that in random Gaussian matrices, this beautiful Wigner semicircle of kind of random, uncorrelated eigenvectors that point every which way. And so you might think that, okay, what matters is when does an eigenvalue associated with an eigenvector which is correlated with the communities, when does that emerge from this so-called bulk of random, essentially random eigenvectors? And when you do this, and again, there are physics papers, and then you can come back into it rigorously. If the graph is dense enough, this coincides with the threshold that we conjectured, which is nice. It's another point that is sort of a algorithm-independent threshold. But for sparse graphs, the standard spectral methods fail. Why do they fail? Well, because if you have a high degree node, and there will be a few high degree nodes in a random graph, there are many ways to take one step away from it and then return to it, okay? And that produces an eigenvector which is concentrated around this, it's localized, concentrated around this vertex. So rather than learning anything global about the graph, like its community structure, you just sort of find this hub, this high degree node. So these localized eigenvectors confuse spectral clustering algorithms. And what they really do is they produce these eigenvalues that leak outside that nice semicircle, okay, and obscure the eigenvalues you want. Well, let's prohibit backtracking. Let's just say you can't do that. You have to find a nice long path around the graph before you return. That way we'll gain some global information. So the non-backtracking operator, which had been, you know, it's also the Hashimoto, so sorry, am I saying that right? Afonso, help me out. I didn't put
Not
it on
sure,
my...
actually. I don't know another
Okay.
name for it.
All right, we were not the first to think of it. But the nice thing is that it delocalizes, it prevents these localized eigenvectors, and as a result, although it is not a symmetric matrix, so its eigenvalues are complex, they now become confined to a circle in the complex plane analogous to that semicircle. And now, again, the threshold for community detection is what we thought it ought to be, namely when the eigenvalue C there with the number 2, that little discrete eigenvalue emerges from this semicircle. So it kind of redeems the spectral clustering approach. So again, this was a lot of fun. In PNAS, a whole crew of us conjectured this, and then a couple of years later, it was proved by some experts in random matrix theory. So I like sociologically this interplay between rigorous and non-rigorous. And by the way, why did we think of this? Remember how I don't pay attention to what Afonso said to me when I decide what to say to him? That's preventing non-backtracking. So if you take the belief propagation update equations, you linearize them around the silly fixed point where everybody is uniform, you find the Jacobian of those update equations, it's essentially the non-backtracking matrix. So that's how we got it. So we're asking when is that silly fixed point unstable? We're turning that into this spectral clustering method, because of course it's a question about the Jacobian of the system in the vicinity of that fixed point. All right, that's all I was going to say. There's lots of other stuff. I would love to tell you about some tensor work that I did with Alex Wine and Ahmed El Alawi, where we have to think about not just pairs, but triples and so on. It's kind of related to a talk earlier in the session. I would love to tell you about that, but I can't. And I just want to say that lots of problems involving noisy high-dimensional data have phase transitions. With physics, you can make conjectures about where they are, and even conjectures about optimal algorithms. And a lot of this can be made mathematically rigorous, but not all of it has been. And mathematical elegance has a lovely role to play, even in the confusing, noisy world of machine learning. So thank you.
Thanks, Chris, for the beautiful lecture. Hey, we have time for a few questions. If there's any from the panelists, you can just unmute yourself. The attendees, please ask it on the chat or raise your hand and we'll figure out a way of promoting you to the panelist room. So while waiting on for questions, let me ask one. Actually, what is known for three communities?
Oh,
Or,
Alan's slide and has some bounds, I think, I think we know that things work out when the degree is large enough for the phylogeny problem, but there are subtle differences between the phylogeny problem and the random graph problem. So I'm actually not sure. I'm sorry.
But it's still expected that below the Kastenstiegen, below, I mean, okay, I guess you didn't mention those words, but below the place where the cavity method works, then you still can't distinguish from an Erdős-Rényi. This is the expectation.
I mean, this is based partly just on numerical results. That yeah, for three groups, if you, I mean, and there are several different kinds of numerical experiments, right? You can do things on large random graphs with 1 million nodes. You can also try to think about the fixed point on infinite trees by kind of trying to solve the distributional fixed point equation you get when you imagine, oh, well, my children would be feeding me messages drawn randomly from a distribution of messages. If I then use the update equation and added my message, which I send to my parent, to this distribution of messages, you can try to do that numerically. And for three groups, for all of these, you don't seem to get this hard regime, because what that corresponds to is more than one fixed point, right? And I'm sorry I went through this so quickly, but remember that picture I drew with the, the amorphous arrangement of the atoms over here and the crystalline arrangement there, or the inaccurate state here and the accurate state there. What this corresponds to in terms of belief propagation is that there are two different fixed points: the silly uniform one that tells us nothing, and the highly accurate one. Both of them are locally stable in this regime. It's just that the accurate one has a very narrow basin of attraction dynamically. What we believe, and this could, we have not yet proved this in the sparse case, what we believe is that an exponentially small fraction of initial states would converge to it as you update things. Okay, so what we see numerically for three groups is no sign of the other fixed point. Specifically, you can test for that by cheating, knowing what you, the experimenter, know about the system. You can initialize the messages very close to the truth. Now, for 4 or 5 or more groups, that initial thing, which of course you wouldn't have access to if you were actually solving this problem, that converges to something quite close to it. But for 3 groups, it just slides over into the useless fixed point.
I see.
So that's, it's just based on that kind of experiment that we don't see any sign of the middle regime there.
But I mean, it could very well be not contiguous to Erdős-Rényi, but still hard to find. Like, we can't rule this out, right? I mean, it's surprising, but not.
Right. There are subtle.
We can't rule it out.
There are some subtle differences between the detection problem, just telling, gee, I mean, we're going to play a game. I flip a coin. I either produce for you a random graph generated from the stochastic block model, the model with communities, or a standard Erdős-Rényi graph with the same average degree. And then I challenge you to figure out which. And so the contiguity issue that Afonso just referred to is that if these two distributions of graphs are contiguous, this is a much weaker property than having small variation distance or something, but it means that any property which holds with probability approaching 1 in one model, in one distribution, also approaches 1 in the other one, which means that I might be able to succeed 60% of the time in telling you whether this was an Erdős-Rényi graph or a block model graph. But there will be no algorithm that can succeed with probability approaching 1 as n goes to infinity. And right, so you can imagine funny situations where I can tell that it's a block model graph, but yet that doesn't help me actually label the vertices. Anyway, so yes, there's lots here to work out.
Yeah, I've always found it surprising that we don't know the case for third communities.
There are a lot of very intuitive things that we haven't been able to prove yet.
What's to be done in the next decade or two? Hopefully by then we'll know how to do all of this.
Absolutely.
Yeah, are there any other questions? Guess we're getting close to the 6 p.m. The whole session was only 20 minutes delayed, so pretty good. 4 talks, 5 minutes per talk delay is quite good. Okay, thanks. All right, if there's no more questions, thank all the speakers again for the wonderful talk. Thank you. And yeah, thank you all for coming.
Thanks for inviting
me. Have a good rest of Friday and have a good weekend.
Thank you.
Yeah, thank you.
So it's great. Excellent session to close the meeting. Thanks.
Thank you.
Thanks.